Hello, this is Z Mathematics and we are doing loci in Argand diagrams today, which is Core Pure 1 Chapter 2. Let's just get into it. So, it looks hard, exam questions look hard, like, what on earth, but it's alright. Hopefully you understand after this explanation. So, these are the types of loci you can get in Argand diagrams. So let's just start with the top one. So, if we have the modulus of z equals r, what does that mean? Well, we know z is a complex number. Let's say x plus iy. R is a constant, it's a number. So what it's saying is that the distance from the origin, as any complex number is measured, from the origin is just r. So if it was like that, that's r. Or if it was like that, that's r. If it was like that, that's r. If it was like that, that's r. It can be anywhere. So if we keep adding like loads and loads of points, you can see it's going to make a circle. So our complex number z, the modulus of z equals r, is a circle centered around the origin with radius r. This is our loci for this. We could also do this by saying, well, we know that z is equal to a complex number, let's say x plus iy. We know the modulus of z is the square root of x squared plus y squared, as if we've got a complex number here, and if the triangle created by it, that's r, that's x, and that's y, well, r is just going to be the square root of x squared plus y squared. And we know that that's a right angle there. So what that's saying is that the modulus of z, which is square root of x squared plus y squared, is r from here. Well, square both sides, we get x squared plus y squared equals r squared, which is the equation of a circle centered origin with radius r. So now what about this? The modulus of z minus z1 is equal to r. So what does z minus z1 mean? It's similar to this, but we're minusing z1. Well, z1, like on the diagram here, is a fixed point. We will know what z1 is, but z is just any point. It can be here, or here, or here, or here, or here, anywhere. So, what is this saying? Well, like, let's say z was over here. So what is z minus z1? Well, if we draw lines from the origin here, we can say, like, this is z1, like a vector, and that's the vector z. Well, z minus z1, if we do z minus z1, well, that is minus z1 plus z. So it's going this way, then here. So the vector goes here. So the vector, if z was over here, it's basically just like the distance there. So z minus z1 is like the distance to where z is. And this distance is r. Again, it's a fixed distance. So if this distance was r, then z would be over here. If this distance was r, z would be over here. This distance was r, this distance was r, this distance was r. You can see what's happening. We're getting a circle around it. So we're getting another circle with the centre of z1 and radius r. And again, what we can do is z is equal to x plus iy. Now z1 would also be, I guess, x plus iy, but x plus iy is just a general complex number. For z1, we can make it a plus bi, and we'll know what a and b are, or we'll have some idea of what a and b are, whereas x plus iy is just general. So what we can say is the modulus of z minus z1, well, that's x plus iy minus a plus bi. Well, if we group the real terms together, what we're going to get is x minus a plus y minus bi. So, like we said earlier, when we're taking the modulus of a complex number, we're doing the square root of the horizontal length and the vertical length. So that's the square root of x minus a all squared plus y minus b all squared, and this is equal to r. And you can see what happens. We get x minus a squared plus y minus b squared is equal to r squared, which is a circle, centre AB, so centre AB, radius r. And the centre AB, well, z1 was a plus bi, so as a coordinate here, that would just be AB. So this loci over here is a circle like this, with the known complex number as the centre. Okay, but now what if we have this? What if we have the same modulus, but instead of it being equal to a constant, it's equal to like another modulus? What does this mean? Well, like we said earlier, z minus z1 is just the distance between z and z1. And similarly, z minus z2 is the distance between z1 and z2. But what this is saying is that the distance here is equal to the distance here. So, like we said earlier, z1 and z2 are fixed points. Z can be anywhere. But where is the distance between z and z1 equal to the distance between z and z2? Well, that would just be in the middle, so like somewhere here. This is when this distance over here is equal to this distance over here. But that's not all. It would also be equal around over here. This distance over here will be equal to this distance over here. And there are different kind of points where z could be, where the distances are equal. And they form this line. Okay, so they form this line. Now what is this line? This line is the perpendicular bisector of the line joining z1 and z2. So this is perpendicular. So this over here, perpendicular bisector, to the line joining z1 and z2. Okay, now what about these ones? These are involving arguments now. So this is the argument of z, which is theta. We know that z is x plus iy, so what we're saying is that the argument of x plus iy is equal to theta. So now, let's say x plus iy was over here. So this is x, this is iy. So what we get is a line with argument theta, just like this. And this is from the origin because we've just got one complex number, x plus iy, that always comes from the origin. But I don't think this is really cared about in mark schemes or anything, but it's actually a half line, so we should have like an open dot here, because when the complex number is 0, it doesn't have an argument, it doesn't make an angle, because it's just lying on the axis, so there's no angle created. So theta would be 0 here, so it's actually a half line from the origin, like this. And what about this? The argument of z minus z1 equals theta. Well, z1 is a fixed point, so I'll just put it over here, let's say. Now, like we said earlier, z minus z1 is like the distance between z and z1. But this is more about the argument. The modulus is more about the distance, but the argument's more about the angle. So if we put z somewhere here, let's say, this is like the distance, but we know arguments are measured from like an axis, but now we're just imagining z1 as the axis. So if we like draw dotted over there, well, the argument of z minus z1 is just going to be this. And remember, it's an open dot here because at the start the argument will be 0, but then as it goes along this line we have an argument greater than 0, so it's actually an open circle and then like that, which is called a half line. So the argument of z minus z1 equals theta is a half line from z1 to z. and we can measure what theta is. So these are what all of the loci are.